into a computer and let it go figure out what the wisdom, what the knowledge is. That idea of scraping the entire internet and putting it in one computer and let the computer figure out what the program is an insane concept. But you wouldn't ever consider doing it unless the marginal cost of computing was zero. And we made that breakthrough. And now we've enabled this new way of doing software. Imagine, for all the people that are still new to artificial intelligence, we've figured out how to use a computer to understand the meaning, not the pattern, but the meaning of almost all digital knowledge. And anything you can digitize, we can understand the meaning. So let me give you an example. Gene sequencing is digitizing genes. But now with large language models, we can go learn the meaning of that gene. We can understand what's the meaning of a cell. A whole bunch of genes that are connected together. And so this is, from a computer's perspective, no different than a whole page of words, and you asked it to summarize. What did it say? Summarize it for me. What's the meaning? This is no different than a long page of genes. What's the meaning of that? Big, long page of proteins. What's the meaning of that? The AI, which was enabled by this new form of computing we call accelerated computing that took 3 decades to do, is probably the single greatest invention of the technology industry. This will likely be the most important thing of the 21st century.
The GPU chip that is behind artificial intelligence right now is your H100, and I know you're introducing an H200. And I think I read that you plan to upgrade that each year. And so could you think ahead 5 years, March 2029, you're introducing the H700.
Right.
What will it allow us to do that we can't do now?
Let me first say something about the chip that John just described. As we say a chip, all of you in the audience probably, you imagine there's a chip kind of like, like this. The chip that John just described weighs 70 pounds. It consists of 35,000 parts. 8 of those parts came from TSMC. That one chip replaces a data center of old CPUs like this into one computer. The savings of that one computer is incredible, and yet it's the most expensive computer the world's ever seen. It's $250,000 per chip. We sell the world's first $250,000 chip. But the system that it replaced, the cables alone cost more than the chip, this H100. The cables of connecting all those old computers. That's the incredible thing that we did. We took this entire data center, we shrunk it into this one chip. The way that this chip works, it works not just at the chip level, but it works at the chip level and the algorithm level and the data center level. It doesn't do all of its work by itself. It works as a team. And so you connect a whole bunch of these things together, and networking is part of it, and it computes at data center scales. And together, what's going to happen in the next 10 years, say, John, we'll increase the computational capability for deep learning by another 1,000,000 times. What happens when you do that? Today, we kind of learn, and then we apply it. We go train, inference. We learn, and we apply it. In the future, we'll have continuous learning. The training process and the inference process, the training process and the deployment process, application process will just become one. Well, that's exactly what we do. We don't have between now and 7 o'clock in the morning, I'm going to be doing my learning, and then after that, I'll just be doing inference. You're learning and inferencing all the time. And that reinforcement learning loop will be continuous. And that reinforcement learning will be grounded with real-world data through interaction, as well as synthetically generated data that we're creating in real time. So this computer will be imagining all the time. It'll do synthetic data generation, it'll do reinforcement learning, it'll continue to be grounded by real-world experiences, it'll imagine some things, it'll test it with real-world experience, it'll be grounded by that, and that entire loop is just one giant loop. That's what happens when you can compute for 1,000,000 times cheaper than today. And so as I'm saying this, notice what's at the core of it. When you can drive the marginal cost of computing down to zero, then there are many new ways of doing something you're willing to do. This is no different than I'm willing to go further places Because the marginal cost of transportation has gone to zero. I can fly from here to New York relatively cheaply. If it would have taken a month, I'll probably never go. And so it's exactly the same in transportation and just about everything that we do. And so we're going to take the marginal cost of computing down to approximately zero. As a result, we'll do a lot more computation.
As you probably know, there have been some recent stories that NVIDIA will face more competition in the inference market than it has in the training market. But what you're saying is it's actually going to be one market, I think. Is there going to be a separate training chip market and inference chip market? Or it sounds like you're going to be continuously training and switching to inference, maybe within one chip. I don't know. Why don't you explain some more?
Today, whenever you prompt an AI, it could be ChatGPT or it could be Copilot. Whenever you're prompting, it's doing inference. So it's generating information for you. Whenever you do that, what's behind it, 100% of them, is NVIDIA's GPUs. And so NVIDIA's, most of the time you engage our platforms are when you're inferencing. And so 100% of the world's inferencing today is NVIDIA. Now, is inferencing hard or easy? The reason why people are picking on inference is when you look at training and you look at NVIDIA's system doing training, when you just look at it, you go, that looks too hard. I'm not going to go do that. I'm a chip company. That doesn't look like a chip. A lot of competitors tend to say, we're not into training, we're into inference. Inference is incredibly hard. The hard part of inference is the goal of somebody who's doing inference is to engage a lot more users, to apply that software to a large installed base. Inference is an installed base problem. This is no different than somebody who's writing an application on an iPhone. The reason why they do so is because iPhone has such a large installed base. Almost everyone has one. And so if you wrote an application for that phone, it's going to be able to benefit everybody. Well, in the case of NVIDIA, our accelerated computing platform is the only accelerated computing platform that's literally everywhere. And because we've been working on it for so long, if you wrote an application for inference, and you take that model and you deploy it on NVIDIA's architecture, it literally runs everywhere. And that takes enormous patience and years of success and dedication to architecture compatibility, so on and so forth.
You make completely state-of-the-art chips. Is it possible, though, that you'll face competition that claims to be good enough? Not as good as NVIDIA, but good enough. And much cheaper. Is that a threat?
We have more competition than anyone on the planet has competition. Not only do we have competition from competitors, we have competition from our customers. And I'm the only competitor to a customer, fully knowing they're about to design a chip to replace ours. And I show them not only what my current chip is, I show them what my next chip is, and I'll show them what my chip after that is. If a customer can do something specifically that's more cost effective, quite frankly, I'm even surprised by that. And the reason for that is this. When you see computers these days, it's not a computer like a laptop, it's a computer, it's a data center. And you have to operate it. And so people who buy and sell chips think about the price of chips. People who operate data centers think about the cost of operations. Our time to deployment, our performance, our utilization, our flexibility across all these different applications, in total, allows our operations cost, they call it total cost of operations, TCO. Our TCO is so good that even when the competitors' chips are free, it's not cheap enough. And that is our goal, to add so much value that the alternative is not about cost. I was hoping not to sound competitive, but John asked a question that kind of triggered a competitive gene. And I came across, I want to apologize. I came across, if you will, a little competitive. But he surprised me with a competitive. I thought I was in an economic forum.
Could you just dive a little deeper into what you see as AI's role in drug discovery?
The first role is to understand the meaning of the digital information that we have. The question is now, what is the meaning of that protein? What is the meaning of this protein? What is this function? As you guys know, you can chat with a PDF. My favorites are you take a PDF file of a research paper and you load it into ChatGPT. It's like talking to the researchers. What inspired this research? What problem does it solve? What was the breakthrough? What was the state of art before then? In the future, we're going to take a protein, put it into ChatGPT just like PDF. What are you for? What enzymes activate you? What makes you happy? And so that's one of the most profound things we can do, is to understand the meaning of biology. Does that make sense? If we can understand the meaning of biology, as you guys know, once we understand the meaning of almost any information that it's in the world of computer science, in the world of computing, amazing engineers and amazing scientists know exactly what to do with it. But that's the breakthrough.
Boy, Oregon State and Stanford are really proud of you. Stanford has a lot of aspiring entrepreneurs, students that are entrepreneurs, and maybe they're computer science majors or engineering majors of some sort.
Please don't build GPUs.
What advice would you give them to improve their chances of success?
I think one of my great advantages is that I have very low expectations. Most of the Stanford graduates have very high expectations. And you deserve to have high expectations because you came from a great school. You were very successful. You're surrounded by other kids that are just incredible. You naturally have very high expectations. People with very high expectations have very low resilience. And unfortunately, resilience matters in success. I don't know how to teach it to you except for I hope suffering happens to you. And to this day, I use the phrase pain and suffering inside our company with great glee. And the reason, and I mean that, boy, this is going to cause a lot of pain and suffering. And I mean that in a happy way. Because you want to refine the character of your company. You want greatness out of them. And greatness is not intelligence, as you know. Greatness comes from character, and character isn't formed out of smart people. It's formed out of people who suffered. For all of you Stanford students, I wish upon you, ample doses of pain and suffering.
I have a couple questions. What's the story about your leather jacket? And the second is, according to your projection and calculation, in 5 to 10 years, how much more semiconductor manufacturing capacity is needed to support the growth of AI?
Okay, I appreciate 2 questions. The first question is, this is what my wife bought for me, and this is what I'm wearing. I do 0% of my own shopping. As soon as she finds something that doesn't make me itch, because she's known me since I was 17 years old. And the way I say I don't like something is it makes me itch. And so as soon as she finds me something that doesn't make me itch, if you look at my closet, the whole closet is a shirt. Because she doesn't want to shop for me again. And so that's why this is all she bought me, and this is all I'm wearing. And if I don't like the answer, I can go shopping. Otherwise, I can wear it. And it's good enough for me. The second question on the forecast is actually I'm horrible at forecasting, but I'm very good at first principle reasoning of the size of the opportunity. And so let me first reason for you. I have no idea how many fabs, but here's the thing that I do know. The way that we do computing today, all the words, all the videos, all the sound, everything that we do is retrieval based. It was pre-recorded. Does that make sense? As I say that, every time you touch on a phone, remember somebody wrote that and stored it somewhere. It was pre-recorded. Okay? Every modality that you know. In the future, most of computing will be generative. Today, 100% of content is pre-recorded. If in the future, 100% of content will be generative, the question is, how does that change the shape of computing? How much more networking do we need? More or less of that? Do we need memory of this? And the answer is, We're going to need more fabs. However, it's not as if the efficiency of computing is what it is today, and therefore the demand is this much. In the meantime, I'm improving computing by 1 million times every 10 years, while demand is going up by 1 trillion times. And that has to offset each other. Does that make sense? That's just a matter of time. But it doesn't change the fact that one day, all of the computers in the world will be changed, 100%. Every single data center will be, all of those general purpose computing data centers, 100% of the $1 trillion worth of infrastructure will be completely changed. And then there'll be new infrastructure built on, even on top of that.
Okay, next question right here, Ben.
Remember, the last question has all big pressure. You guys agree with that? Can we all agree?
Right here.
The person who asked the last question, don't leave us all depressed.
I'm going to invoke your commitment to have low expectations at this juncture. You mentioned you're competing with your customers, and I'm wondering, given the advantages that you have, why they're doing that. And I'm wondering if in the future you see yourself building more customized solutions for customers of a certain scale, as opposed to the solutions that you have now, which are more horizontal.
Are we willing to customize? The answer is yes. Now, why is it that the bar is relatively high? Because each generation of our platform, first of all, there's a GPU, there's a CPU, there's a networking processor, there are 2 types of switches. I just built 5 chips for one generation. People think it's one chip, but it's 5 different chips. Each one of those chips are hundreds and hundreds of millions of dollars to do. Then you've got to put them into a system. You've got networking stuff, you've got transceiver stuff, you've got optics stuff, you've got a mountain of software to do. It takes a lot of software to run a computer as big as this room. And so if the customization is so different, then you have to repeat the entire R&D. However, if the customization leverages everything and adds something to it, then it makes a great deal of sense. Maybe it's a proprietary security system. Maybe it's a confidential computing system. Maybe it's a new way of doing numerical processing that could be extended. We're very open-minded to that. Our customers know that I'm willing to do all that, and recognizes if you change it too far, you've basically reset, and you've squandered, the nearly $100 billion that's taken us to get here, to redo it from scratch. And so they want to leverage our ecosystem.